This video is for Math 0242-1342. We previously covered 9.1 and 9.2 during the third unit, so now we're going to pick up and do 9.3 and 9.4 to start the fourth unit. And then we also cover chapters 10, 11, and 12, a little bit of each of those chapters. So 9.3 is very similar to 9.2, except 9.2 you always know the population standard deviation sigma. So when sigma is known, population standard deviation, then you have some kind of z situation like a z interval or a z-test. And if you go for critical values, you'd go straight to the bottom of page 7 anytime it's a z type of problem. When all you know is S, sample standard deviation, then that's when sigma is unknown, and then you have a t type of situation. T interval, t-test, and then critical values go inside page 7 to the degrees of freedom. So here they want me to do critical values for the student t's distribution table. We're told in part 1 that alpha is 0.025, n is 12, and the alternative hypothesis is a greater than situation. So whenever you're doing confidence intervals, critical values are automatically positive. When you do hypothesis testing, they can be positive, negative, or both, like they have right here, plus or minus. But if the alternative is greater than, then you get a positive critical value only. If it's less than, you get a negative only. And if it's not equal to, then it's plus or minus. Also, if it's just greater than or just less than, then this whole alpha goes in the one tail that we care about. So on problem 1, alpha is 0.025, and the alternative hypothesis has a greater than. So then we're on the greater than side of the curve, and we put the whole 0.25 in that tail. So this is one, it's definitely going to be a positive t critical value, and it's 0.25 in one tail. So if you go to page 7 of the formula sheet, look for area in one tail and 0.25 in one tail. It's this middle column. Since the sample size was 12, I have to go to 11 degrees of freedom, 2.201. And then it's just positive that automatically. 2.201. If the alternative had been not equal to, and n was 26, then you're going to use 25 degrees of freedom. But whenever it's not equal to, then you're definitely going to get plus or minus whatever it is. And whatever alpha they give you, you have to cut it in half. So two-tailed, you cut alpha in half. If it's either of the one-tailed ones, you don't cut it in half. So if I divide this by 2, then it's 0.005 goes in each tail. There's 0.005 down here, 0.005 up there. There'll be both a negative and a positive critical value. And I can either say that there's 0.005 in one of the tails, or combined together it's 0.1 in both tails. And n was 26. N was 26, so the degrees of freedom would be 25. So I have 0.005 in one tail, which is right here, the first column, or it's 0.01 combined in both tails. And then go to 25 degrees of freedom, 2.787. But plus or minus 2.787. So if you were going to use the test statistic instead of the p-value method, 2.787 negative and positive. If you can land in one of these two tail regions, which are called the critical regions, or some people call them a rejection region, if you get a test statistic that's greater than this 2.787 or less than this negative 2.787, then you're in the critical region and you reject the null. But if you land in the middle portion of the graph, then you don't reject the null because that's not an unusual area to land. Okay, so a test is made of the null hypothesis is that mu equals 76. The alternative is that it's less than 76. There's a sample size of 16. The sample mean and standard deviation are 68 and 5, and notice it's S. S equals 5, not sigma equals 5. So that's a t-test for sure. Compute the value of the test statistic t. So I could just run this in the graphing calculator and go to stat tests. The only one you learned of the test was the z-test in 9.2, but t-test is very similar, just the same way t interval is very similar to z interval. So choose this one. Okay, you can do data or stats. We'll see a data problem eventually, but most are stats. Mu 0, that was the number from the null hypothesis, which was 76. Mu 0. Okay, wait, gotta go back to the calculator. 76. The x bar was 68 and s was 5. 68 and 5. The sample size was 16. And we had the less than alternative, which is this one in the middle here. Calculate and you'll get the p-value and the test statistic. The p-value is this 5.97 e negative 6. That's very low. The test statistic is negative 6.4. And z-scores and t-scores, usually they don't go past 3 or negative 3. This one's all the way down at negative 6.4. So the test statistic is negative 6.4. This would certainly land in a rejection region and a critical region if you were doing the critical value method. Is H0 rejected at the 0.05 level? That's where you would use the p-value. And the p-value in the calculator was 5.97. Remember that probability can't be bigger than 1, so if you see 5.97, make sure you look all the way at the end. There's an e negative 6 at the end. This happens on cases where the claim is like really way off, and it's very unlikely that that null could be true. So you have to move the decimal 6 to the left, which actually makes it have 5 zeros in the decimal. 0, 0, 0, 0, 0, 597. This is virtually equal to 0. It seems students think it's close to 6, but it's nowhere close to 6. And in fact, 6 is impossible anyway. If you round to 4 decimals, it's virtually equal to 0. So, and then alpha's 0.05, but it wouldn't even matter which alpha they give me. Alpha's 0.05. But 0, 0, 0, 0 is definitely less than 0.500. The p-value is less, the p-value is low, so the null must go. Reject the null. And even if we did the critical value method, for sure that test statistic of negative 6.4 would be way past whatever critical value you would have. So both methods would say reject the null. If you reject the null, then, oh no, this is a different, they're not doing the normal steps right now. Would it still be rejected if alpha was 0.01 is what they're asking here, and yes, it would be, because 0 is less than any alpha they would ever give me. This is a very extreme test statistic. Getting negative 6.4 doesn't happen very often. So what this is saying is this average of 68 in the sample, that is significantly less than 76, very significantly less. The probability of it occurring is virtually 0. if we assume the null to be true, that the mean really is 76, there's virtually a 0 probability that a sample mean would be 68 is what this is saying. So that's why we reject the null. Okay, so that wasn't the full process that we normally do, but here they're doing it here in number 3 now, because I can see part 1 of 5, so that's when you do all the steps. So this is going to be very similar to the problems that the last unit ended with when we were in section 9.2 and we were doing the z-test. This is going to be a t-test though. So there is a random sample of 53 family practitioners in Los Angeles, and the sample of 53 had a mean of this with a standard deviation of that. So this is definitely a t-test because the standard deviation is coming with the sample information, and therefore we only know S and we don't know sigma. There was that first sentence had this number of 178,258. That's going to be the null hypothesis. A null is usually that very first sentence. So supposedly the mean equals 178,258. But then we got 191 in the sample. So is that some kind of evidence that the null is wrong? Do the data provide sufficient evidence to conclude the mean salary for practitioners in Los Angeles is greater than the national average? So the alternative is that it's greater because we got some value in our sample that seems to be greater. Since this is greater than, that's right-tailed, and you could do a critical value with a right critical value only, a positive critical value only if you want to do that method. So now run a t-test in the calculator. Stat tests, number 2 t-test, because we don't know sigma. The mu0 is right there, mu0, 178,258. 178,258. X bar was 191,410. See, the sample mean seems to be significantly higher than the claimed mean for the whole nation, so that's why somebody thinks it's greater, but maybe that's not that significant. You can never tell just from the raw numbers alone, but that kind of seems quite large, although the standard deviation is quite large too. 43,017 is the standard deviation. 43,017. The sample size was random sample of 53. And then we had greater than for the alternative, so that's the far right option. Move this over to the far right and click it and then calculate. The test statistic is 2.23. The p-value is 0.152. That's going to be the next 2 parts. So part 2, you put 2.23 for the test statistic. The z-scores and t-scores, when you're doing test statistics, if you get like 0 point something or 1 point something, those aren't that unusual. Once they start becoming 2s and 3s or even 6s like the previous problem, then you start getting unusual ones that are way out in those rejection regions, and that makes the p-value get lower and lower. So the p-value was 0.152, which would be less than any alpha they would give us except for the 0.01 alpha. So we got to see if we get 0.01 or not. Determine whether to reject the null. What was alpha? Alpha was 0.10 actually. So the common ones are 0.01, 0.02, 0.05, and 0.10. Alpha is always between 1 and 10%. So I just got a p-value of 0.152. The given alpha is 0.10. Now don't say 152 is greater than 10 because you got to add 2 zeros first. 152 is actually less than 1,000. The p-value is less, the p-value is low, so we reject the null again. So we are saying that this 191,000 is significantly greater than the 176,000 that was supposed to be the national average. So apparently in Los Angeles, they are significantly greater than for their salaries. But their cost of living is higher too. So reject the null since the p-value is low. And there is enough evidence to say that the practitioners in LA are greater than the national average. So the good news is all the part 4s and 5s are done exactly the same way as the other one you learned from the previous test. Every part 4 and part 5 is done exactly the same way in every hypothesis test we're going to learn over the next couple of chapters. And even the t-test statistic and the p-value, you just run it in your calculator. It's very similar to the other one. And the null is basically the same thing too. You're working with the mean, and is it equal to something in the null, and is it greater than, less than, or not equal to in the alternative? Here's an example of data. They're giving me all the raw data. So just so you see an example of this, I usually don't put these on test just because they take a while to type in. And if you have a typo, then you get every answer wrong, unfortunately. But go to Stat. And while it's on Edit, press Enter. And then you're in these spreadsheets. And if you still have data there, go all the way up to the top and hit Clear Enter. Now type in 409 and press Enter. And now that's the first entry, 409. I wanted to leave this so I could see both at the same time, but now I can't see what I'm typing in there. Let's 550, 1299, and go up and double check those are there. Yeah, 550, 1299, 353, 610, 814, 353, 610, 814. So if you have the slightest little typo, then every answer you do after this will be wrong, unfortunately. 386 and 1513. So even though there's 2 rows, we're going to put all these into list 1. So keep going. 688, 688, 1567, 979, 2258, 2482, 1753, and the last 2 are 1674, 528. Okay, so once all the data's in there, then you go to Stat, Tests, t-test, because I clearly don't know sigma unless they tell it to me, and they don't mention it here anywhere. And this is when you go over to data. While it's flashing on data, press Enter. So now data selected. We still have to do the mu0 from the null hypothesis. That's this part here. It says, according to the report, the mean outstanding balance for college seniors in a recent year was 525. So the mean was 525. That's the null. We want to see if it's less than 525 in the alternate. And less than's a left-tailed test. So then if we did the critical values, we'd get a negative answer only. So in data, you still have to tell your calculator the null is 525. So come down here to mu0 and mu0, 525. but you don't have to fill in the X bar or the S or the N. All that is done for you from the data. The list can be L1 through L6, wherever you want to put your data. I usually just put it in L1. The default's L1. So if you put the data in L1, then you don't have to change that. Frequency defaults to a 1. I know the answers work if you leave that as a 1, and I don't actually know what would happen if you change it to something else, but leave it as a 1 and it'll work. And here's less than here, so I need to pick the less than 1 right here in the middle. Whoops. Go up, and while it's flashing on less than, then press enter. Now that one's selected. Go down, and while it's flashing on calculate, press enter. There's the test statistic for step 2, and there's the p-value for step 3. The test statistic T is 3.44. Oh, they want 3 decimals now. 3.4. Usually they like 2 for this one. 3.436. And the p-value is extremely high, 9982. So now we got to compare 9982 to the given alpha of 0.01. (9982) compared to an alpha of 0.01. Well, that's way greater. 9,000 is way greater than 100. It would be greater than 1,000 or any other alpha they would give me. So this p-value is always greater than any normal alpha from 0.01 to 0.10. When the p-value is less or the p-value is low, the null must go, but this p-value is not less, it's not low, so the null does not have to go. Do not reject the null. That means there's not enough evidence to say it's less than. Not goes with not. So do not reject the null. Not enough evidence to conclude the mean is less. So data problems work like stats. It just takes a while to type them all in, and then if you have the slightest typo, then you'll get every answer from part 2 all the way down wrong. So that's why you can do them, and real statisticians actually work with data. They don't have somebody telling them this whole paragraph of information here. Like number 3, how they summarize all this for me, these stats that are given to me. Most problems are done that way in the textbook, but if you're a real statistician, you don't have anybody doing that for you. So real statisticians do the data type more often than the stats, but for us, we usually do the stats one. Okay, the big difference here now is now we're switching to percentages or proportions. These are going to come from yes/no questions. A researcher reported that 71.8% of all emails sent in a recent month was spam. So you put P instead of mu, and you really can't mess it up because they don't give you a chance to put mu accidentally. Same rule that you put equal to, and then always change percents to decimals, so 0.718. If you don't make it 0.718, they'll count it wrong. And then in the question part, it says, can we conclude the percentage of emails that are spam is less than 78%? Oh, wait, no. Okay, so see, the numbers didn't jive there. You shouldn't have one that's 718 and another one that's 78. But notice there's a second sentence that says a system manager at a corporation believes the percentage at his company may be 78. So that kind of supersedes the first question. The claim is that it is 78, and then later we want to see, is it less than 78 maybe because of this number. So it's definitely less than, though, so this is definitely a left-tailed test. But the two numbers here should always be the same. You would never put 71 in one of them and 78 in the other. And once the question said, is it less than 78, I knew that had to be right here, so this had to be equal to 78 then. Okay, so then this is about P or proportions, yes, no questions. Either the email is spam or it's not. So when you go to the calculator, stat tests, this is the fifth one that's called one prop Z interval. It's kind of similar to when we were doing the confidence intervals and we had Z or T intervals for means. Well, now we have Z or T tests that are like that. And then we could also do letter A, if you remember, one prop Z interval. Now we're doing a one prop Z test. And just like the intervals, there's no data or stats to worry about. There's no sigma known or sigma unknown. There isn't even a sigma here. First, we need P0, which is the one from the null right there. P0 is 0.78. I got to put, see, this is where you need to put 0.78. If you put just the 78 from the percentage, if you put 78 from 78%, it'll give you an error message. So you always need this as a decimal. And then there's X and N. That's the number of yeses and the sample size. Well, clearly it says here, he examines a random sample of 500 emails. That's clearly N. So go down to N and put 500. There'll only be one other number in the whole problem, and that'll be X. How many of these 500 were spam? He finds that 370 messages are spam. So that's the X, 370. And remember, X can never be bigger than N, even when you're doing confidence intervals. So we checked 500 emails, and yes, 370 of them were spam. We're trying to see if they're less than 78%, so then I'm going to leave this on less than, and hit calculate. So proportions are always nice because it's the easiest ones to do. There's less stuff to type in. You don't have to worry about data or stats or sigma or S. And it's just how many people say yes, how many total were sampled, and what's the null and alternative. So the test statistic is negative 2.16, or maybe they still want 3 decimals, 159, 2 decimals again. So I'm going to make it negative 2.16. And then the p-value is 0.154. So if alpha is 0.01, I would get a different answer than if it's 0.02, 0.05, or 0.10. So sometimes it depends which alpha they give you, how the ending's going to go. Here they want me to use both 0.1 and 0.5. Normally you just do one of them, but again, they're trying to show you that, yeah, if you switch this to something else, it can be a different answer, actually. If I use 0.01 first, if we do the 0.01 alpha first, I just got a 0.154 p-value. If I use 0.01 as alpha, even adding 2 zeros doesn't make it get smaller, it's still greater. 154 is greater than 100, so this one you would say do not reject the null. And then there would be not enough evidence. But if you do the one where it's 0.05, then adding 2 zeros makes a difference. And now you have 154 is less than 500. Then you reject the null. Changing alpha after the fact, after finding out what the p-value is, can completely make the conclusion go the other way. You can go from a not guilty to a guilty in court. When I was getting my master's degree, the professor we had for statistics, he used to be called in by lawyers as an expert witness in trials. And he would run these hypothesis tests and show whether the probability of what they saw was common or unusual. And he told us that shady lawyers would sometimes try to bribe him to switch this alpha from 0.01 to 0.05 or vice versa to make it come out in favor of their client. And luckily for him, the court sets this. Usually if you're like in a criminal trial, they'll do the lower one, because then you have less of a chance of making a type 1 error and putting an innocent person in jail. And if it's a civil trial just suing for their money, then they raise it up higher. So that was always determined by the court ahead of time, and if he tried to switch it, the judge would know, and he would go to jail for taking the bribe. So luckily he would have to tell them, I can't take the bribe, or the judge will instantly know, and I'll be in jail. So if alpha was 0.01, then you do not reject the null. And that's like finding somebody not guilty. If alpha is 0.05, then you reject the null and you find them guilty. It can be that close, actually, literally. So if you had the 0.01 example where you did not reject the null, then there's not enough evidence to conclude that we're less than 78%. But if you did reject the null from a 0.05 level significance, then there is enough evidence. It can be that close where it makes it completely go the other way. So the alphas are always determined ahead of time to make sure you're not just picking it the way you want it to come out. And they usually don't do 2 in one problem, but I guess that's the point of this, is to show you how just switching that from one little alpha to another, and it's not even that far of a switch, can completely change the outcome of the whole thing. Okay, here's a second example of one of these. The Gallup poll asked 1033 U.S. adults, so there's N, that's a sample size, whether they believe that people should pay sales tax on items purchased over the internet. You see, it's a yes-no question. Either you say yes or no to that. And then it says, of these, 434, there's your number of yeses, said yes, they support this tax. Does the survey provide convincing evidence that less than 46% of U.S. adults are in favor of this? See, less than 46%. That's clearly the alternative. The proportion is less than 46%, which means 0.46. And in the null, you always put equal to no matter what. So that's definitely the same number, and it's equal to. We have less than for the second time in a row, so that's left-tailed again. Run a 1 prop z-test, because this is about proportions for sure. Okay, I was having a hard time making the calculator show up, but I discovered if I lower it way down here, then you can see the screen. But then I can't see all the buttons is the only problem. So stat, tests, go down to number 5, and now I have to scroll down so I can press enter. Scroll back up. Okay, 1 prop z-test. So put this 0.46 in for P0. That's P0 right there, P0. P0 is 0.46. The X was that 434 right at the end of the first line. 434 said yes, they support this tax. There was 1,033 people surveyed. So less than half were in favor of this, but some people wanted them to raise money this way to pay for things. And we're going to keep it on less than for the second or third time in a row. So I've got the P0 from the null, I've got the number of yeses, the sample size, and the alternative is less than. Then press enter while it's flashing on calculate, and you'll get your test statistic and p-value. The test statistic is negative 2.57. Whoops. So we're getting out there close to negative 3 now. This is starting to become an unusual test statistic. It would probably be in the rejection region, or the critical region they call it. And because it's starting to get way out there, that's why the p-value is so low. This p-value was like 0.0 something, if I remember right. 0.051. 0.051. Well, this is less than any alpha they would give us. So even if they make me do both 0.01 and 0.05 again, I would be less than both of those. But this is a more normal problem because all they have is, it says use a alpha of 0.10 over here. Use alpha 0.10 level significance. So write the p-value down first every time. When you're doing these conclusion parts, always put the p-value first. 0.0051. Then put whatever alpha they give you next, 0.10. Don't get tricked and say 51 is greater than 10. Some people do that. You got to add 2 zeros here so they both have 4 decimals. 51's actually less than 1,000. The p-value is less, the p-value is low, so the null must go. Reject the null. And if you reject the null, there definitely is enough evidence to say it's less than whatever it was. So anytime you reject the null in part 4, then there is enough evidence in part 5. If you do not reject the null in part 4, then there's not enough evidence in part 5. Reject the null. There is enough evidence to conclude that less than 46% of U.S. adults favor an internet tax. So if like Congress or some state government wanted to do this, they probably would not want to do it unless more than 50% were in favor of it. So then they'd probably back off and not do it, or people might get mad. Okay, one more example here. We have a Forbes magazine reported that 73% of small businesses advertise on social media. So that's probably the null that P equals 73% or 0.73. Unless they like change it later in the paragraph somewhere. An economist thinks the percentage is higher. So that's the alternative, that he thinks it's higher than 0.73. Or she, I guess. So she samples 70 stores and finds 57 of them advertise on social media. See, there's your N, your sample size 70. And 57 said, yes, we do that. Can she conclude that more than 73% of stores advertise on social media? More than, which is greater than. So that's a right tail test. Use alpha 0.05 and the p-value method, okay? So go to stat tests, one prop z-test for the 3rd time in a row. P0 is this right here. P0 is 0.73. X is the 57. The ones that said yes. N is the sample of 70. 70. Enter. And because we put greater than in the alternative right there, greater than, now I have to switch this because I've been doing less than for like 2 or 3 problems in a row. So go over to the far right where greater than is and press enter. And calculate. So now the test statistic is only 1.588 or 1.59. 1.59 isn't too extremely unusual, but maybe it can depend on the alpha if we end up rejecting it or not. In fact, we have an alpha of 0.05 right here. And our p-value is 0.0561. 0561. See, that's right smack dab in the middle of possibly rejecting it or not. If I get 0.01 or 0.05, I'll get a different answer than if I get 0.10 actually. Which alpha they give me can make a difference on how step 4 and 5 go. So write your p-value down first. 0.0561. The given alpha is 0.05. Add 2 zeros to it. 561 is greater than 500. The p-value is greater than. It's not less, it's not low, so do not reject the null. Which means in the final step, there's not enough evidence to say it's greater than whatever. So do not reject the null hypothesis. Although if alpha was 0.10, you would have rejected it. And then there is not enough evidence to conclude that more than 73% of stores advertise on social media. So problems 5, 6, and 7, they're all from the one prop z-test part of the chapter. Okay, you can also do confidence intervals for these things. So notice here there's a double box waiting for a confidence interval. And it's mu1 minus mu2, so we're back to doing means. This is a difference between means. There's a group of 76 people enrolled in a weight loss program that involves adhering to a special diet and to a daily exercise program. After 6 months, their mean weight loss was 22 pounds with a sample standard deviation of 10. Well, sample standard deviation, we're definitely doing a t-test. There's a second group of 43 people that went on a diet but didn't exercise. So their mean weight loss was 12 and a sample standard deviation of 6. Construct a 99.5% confidence interval for the mean difference in weight losses. And mu1 is the group that did the exercise. Well, we did, if I come back here and make it visible, we did stat test. We've currently learned z-test, t-test, and one prop z-test. In the previous test, we haven't learned the 3, 4, and 6 we're going to learn in the next chapter, actually. We previously learned z-interval, t-interval, and one prop z-interval on our previous unit, our previous test. But we didn't do 2 sample z or 2 sample t or even 2 prop z yet. These are taught now. So this is definitely a 2 sample t interval t because they said sample standard deviation. So I'm going to choose number 10, the 2 sample t interval. And just like the test, you can do data or stats. I'm going to go over to stats because that's all the information in the paragraph. And now you just fill all this information in. So the first sample mean was this 22 right here. Their mean weight loss was 22. The first group had a mean in the sample of 22. With a sample standard deviation of 10, so that's definitely S1. And that was a group of 76 people. So the first N1 is 76. The last test you just took had a problem that just stopped right at that point. So the only thing different here is we're doing 2 at the same time. Now there's a second group of 43 people. They went on the diet, but they didn't exercise, and their sample mean was 12 instead of 22. Theirs was only 12. Maybe 22 versus 12 is a significant difference. Seems like it is. It's almost half. And their standard deviation, they had a sample standard deviation of 6. And they had 43 people for N2. So we have 2 means, 2 standard deviations, and 2 sample sizes. Then they want me to do a 99.5% confidence interval, so make the C level 0.995. 0.995. And then pooled, yes or no. This is the same thing as before. So unless they tell me that I can assume the variances are equal, then I'm going to assume that it's no. And I don't see it saying that anywhere. Yeah, so if it doesn't mention it, then you just assume no. You can only say yes if they say assume the variances are equal and they're not even mentioning it here at all. So I'm going to keep it on no for pooled. And calculate. Round to the nearest integer. So 5.8 would round to 6. And 14.1 would round to 14. So the difference in the means we think is somewhere between 6 and 14. And because that's all positive, that means that the first people lost significantly more weight than the second people did. So the exercise helped. We could say, yes, the diet helps, but the exercise helps too. So the people that did diet and exercise lost significantly more weight than people who only did the diet. Okay, this is definitely a data problem, but it's still a confidence interval for a difference between means. When data is given to you, it's almost automatically going to be a t because they would have to tell me sigma, and I don't see sigmas anywhere here. In theory, they could tell you sigma, but they literally would have to tell you sigma for you to do a z, so this is a t again. And I just have to do data. That's a little hard to put this so I can see it and type it. Stat, press enter for edit. Go into the spreadsheet and let's clear out this list by going up to where the L1 name is. You need to up arrow to where L1 is. And then hit clear, clear, enter. That wipes out the old data. Don't hit delete, otherwise the whole list disappears. So now my L1 is blank. I'm going to put the online people in L1 and then we'll put the classroom people in L2. So it's a little hard to type this and see it at the same time. Okay, 65, 74, 84, 63, 87, 76, 73. Now, even though there's a second row, keep going. 90, 71, 68, 76, 82, 61, 69. Okay, so all those online scores went in L1, and then you're going to put all the classroom scores. I think it's a little wider, yeah. So then put all these in L2. 70, 79, 55, 74, 82, 70, 80, 73, 77, 54, 82, 80, 81, 68, 58, 69, and 92. These are not matched together. These are not like before and afters. So the data don't have to be side by side with each other. And in fact, one can have a larger sample size than the other. So once I see that I'm doing a confidence interval for a difference in means, definitely a confidence interval. It even says confidence interval. 90% is the C level. There's two answer boxes with a double less than. That's definitely a confidence interval. Stat, test, it's one of the intervals. But since there's two sets of data, it's a two sample interval. And it's about means, so it's got to be Z or T interval, not proportions. And it's T because we don't know sigma. We only know sigma really if they tell it to us. And in this paragraph, it never mentioned it. So the difference here is now you're going to click data instead of stats. So the defaults are usually good. The L1 and L2 is definitely where I put my data. Always leave the frequencies as 1. I don't even know what happens if you change those. But the C level wasn't 995 this time, it was 90. So change that to 0.90. Pooled's always going to be no unless they somehow tell me to assume the variances are equal, and I don't think they're mentioning it in this chapter. They did mention it in the last chapter when we were doing tests, but I don't see that anywhere here. See how they say assume the populations are normal. Usually that's where they would put that. And assume the variances are equal, assume the variances are unequal. If they don't mention that, then you just assume they're not. And I don't see that anywhere else, so I'm going to keep it on no. No to pooled, and then calculate. And these are just confidence intervals, so you're not doing the 5 steps. It's just all about the final answers. So now the first answer, how far they want it rounded? Round to 1 decimal place. Negative 4.8. And positive 6.9. Okay, so there's a part 2 coming up, and so if you think about that last answer we had, remember the last answer was like 6 to 14? On the previous problem, I got a confidence interval that was 6 is less than mu1 minus mu2 is less than 14. So what this is saying is when I subtract the two means, the answer is always between 6 and 14, which the more important thing is it's always positive. And if the answer is always positive, that means the first thing is bigger than the second thing. When you subtract, if the first number is bigger than the second number, that's how you get a positive answer. And if the entire interval is positive on both sides, then you know the first one's bigger than the second one. It's significantly bigger. If the two answers were both negative, then you would know the second one is bigger and the first one would be smaller. But when you get a case like this, where one answer is negative and one answer is positive, on the next problem, I got negative 4.8 to positive 6.9. Well, because 0 is inside this interval, 0 is between negative 4.8 and positive 6.9. So therefore, if the answer is 0, that would happen when mu1 equals mu2. If the two means were equal and you take two numbers that are equal and subtract them, you get 0 for an answer. So anytime a confidence interval for these difference in means or proportions contains 0, then we don't have evidence against the null. The null always says they're equal when we're doing hypothesis testing. And if they're not equal, that's the alternative. And that's when you reject the null. So if 0 is a possibility, then I can't say that one of these is better than the other or that one's higher than the other. An educator claims both methods are equally effective. See, that's if they're equal, that's when 0's in the interval, that means it's possible that they're equal. Does the confidence interval contradict this claim? No, it doesn't, because 0 is possibly in my interval. It would only contradict it if 0 was not in the interval. In other words, if it was all negative for both answers or all positive for both answers, then you could say it contradicts the claim. So in these confidence intervals, when there's two means or two proportions, there's probably one with two proportions too, then you're trying to see if 0's in the interval or not. If 0's in the interval, then that means these two things could be equal to each other. If 0's not in the interval, then one's higher than the other and 0's not in there. Okay, so let me give you, here's another one with difference of two means. So before we do this problem, let's do a magic word of this video, and we're in a new unit now, so I'm going to do a different theme this time. Let's go ahead. I was trying to think of a different theme today, and I didn't think of anything great, so let's just do the month of the year. And the first one will be the month we're in right now. So the first magic word of Unit 4 is November. So this looks very similar to the previous problem. I have the difference in means right here. It's an 80% confidence interval for the difference between men and women and their mean number of energy drinks. There's a survey of 416 male college students, and they had an average of 2.47 with a standard deviation of 4.90. So the standard deviation is with the sample information. So this is a sample standard deviation, and therefore I'm doing a t-test, a t-interval again. Then there's a sample of 364 female college students, so a second one, and they have an average with a standard deviation. So this is another t-interval, two-sample t-interval. And we're back to doing stats instead of data. So stat tests and go down to the two-sample t-interval. They don't have an example of two-sample z. So all three times we did this, it was two-sample t-interval. The first time we had stats, the second time we had data. Now we're back to doing stats again. So X bar 1 is the first average, which is 2.47. With a standard deviation of 4.90, so that's the first S, 4.90. That came from a sample of 416 male students. Then the second sample average was 2.22, which doesn't seem to be all that far away from 2.47, but maybe that is a significant difference. The second standard deviation is a little off the screen here. It's 3.32. And they had 364 in their sample. So it doesn't matter if the sample sizes are different or the same. And then I think it was 80%. Yeah, see, 80%. So I need to change the C level to 0.80 or just 0.8. And probably no to pooled. Does it say anything about assume the variances are equal or unequal? No. When they don't mention it, then you just say no to pooled. And calculate. And we're going to wonder if 0 is in the interval. And 0 is in the interval because the first answer is negative and the second answer is positive. Round to 2 decimal places, so I'm going to put negative 0.13 and positive 0.63. Negative 0.13 and positive 0.63. Because 0 is in that interval, then it's possible these two groups are equal. The men and the women could be equal in their energy drink consumption. Based on the confidence interval, is it reasonable to believe that the mean number of energy drinks consumed may be the same for both men and women? It is reasonable to assume that because 0 is in the interval. And if 0 was the answer, that would mean they're equal to each other. If you do the men minus the women and get 0 for an answer, that's when the two numbers are equal. So number 10, 9, and 8 were all these two-sample t intervals. After we did 7, 6, and 5 were all t intervals. T-tests, I'm sorry, two-sample t-tests. Oh, they were the proportion ones. Okay. So now they want me to do Minitab output. This is a computer program that will do this too. So what's the point estimate? The point estimate is the estimate for the difference. So it should be this 20.7429. Point estimate, just look for the word estimate to find that. The number of degrees of freedom is listed right here, 30. We are blank percent confident. Okay, where's the confidence level? 98% confidence interval. So we are 98% confident that the difference in the means is between blank and blank, and that's the answer right here, like the calculator spits out too. 12.9408 and 28.5450. So this is all about just reading technology instead of using a graphing calculator. There's some people that use Minitab to do this instead of a calculator. Okay, mean difference. I think this homework might be mislabeled. Okay, because it says, not, is there a 10-1? Let me go back to Alex real quick. That's weird. And, oh, maybe this goes into chapter 10. Okay. Okay, so 9, 3, 9, 4, 10, 1, 10, 2, 10, 3, 11, 1, and 11, 2, 11, 3, 12, 1, 12, 2, and a review, which isn't even here yet. So my original plan was to do a video for 9, 3, and 9, 4, because that's what we're doing at the end of the week where the third test is. And then the following week starts with 10, 1, and 10, 2. And then there's a, well, do I have the calendar here? No, I don't have it in front of me. So I don't want to go farther than we need to is the thing in this video. And sometimes these homeworks tell you which chapter they're from, but this one's not telling me that. So let's see, in Alex, can I go back to the home page? Here's the book. It's going to take too long. Let's go to confidence interval for the difference between two means. Yeah, I'm doing some chapter 10 stuff right now. Okay. So I wasn't sure when chapter 9 ended. 9.4 was hypothesis test for proportions. So 5, 6, 7, I think that was 7. Yeah, that's proportion. 8. Okay, so yeah, I thought this was still part of that chapter, but it wasn't. Okay, so technically you only need to do 1 through 7 to get through chapter 9, and that's what this video was supposed to cover actually. And then I was going to do a second video for 8 through 15, but since we're already over an hour anyway, at least you got a little bit into the next chapter already, so, and maybe I can do one more example of this in the next video. So I'll have another video that'll cover one more example of 8 through 10, and then we'll do 12 through 15 as well. And I'm just trying to keep it to where we have 5 videos again in every unit. So there'll be, where was I on here? Alex. Okay, over to the assignments. The 5 videos of this unit are going to be 9.3 and 9.4 is 1, even though this homework's together. 10.1 and 10.2. That'll be the second one. Then there'll be a third one for 10.3, 11.1, and 11.2. A fourth one for 11.3, 12.1, and 12.2. And then a review. The review will be added here soon, but that'll be the 5 videos instead of having just 4 of them. And that way we don't have to have one video that's covering 4 sections when that's over a couple of 2 different weeks where that's even going on. So we'll go ahead and stop this video for, it was only supposed to be 9.3 and 9.4, which are problems 1 through 7. And then I actually did all the way to 11, but at least you got more than you needed here, and we can always do some more examples in the next video too. So that's it for this one.